Any questions?
Yeah, when I was doing the lab yesterday, the one from last week, the two questions about deriving the two equations from the equations given, can you just do, I don't know, it doesn't have to be the exact one, just show how to derive things, just an example of deriving something. Because I kind of get what you're doing, it's just hard for my brain to wrap around that idea.
All right, so it comes down to, for any linear plot,
Mhm.
or what we expect to be a linear plot, given the slope and an intercept,
Mhm.
I know that if that's my y and x axis, I can put it into slope, it's called slope-intercept form.
Mhm.
All right, I assume you're good with that.
Yes.
So whenever I'm deriving anything, I'm trying to get it into that form.
Okay.
So if I have, we'll just take something from a while ago, F equals ma,
Mhm.
and this is acceleration and force.
Mhm.
Well, I'm trying to isolate, as I have y isolated here, I would try to isolate a. So I'm trying to get it into a equals something times f, since that's my x value, plus something.
Okay.
Well, if I'm isolating a, I have to divide by m.
Mhm.
And take it that one step further to put it in that form, I know that's 1 over m times f. So therefore, 1 over m and 0.
Okay.
And almost everything we do, it's gonna be plus 0. There's an optics experiment where it's not, and we can, I guess officially with the slinky, since I had you map first position instead of displacement, that would also have an intercept.
So whenever we're deriving anything, not just for the certain lab or anything, you try and use the graph formula or the slope formula?
Yes.
Oh, okay.
Yeah.
Okay. That makes sense. Thank you.
Okay. Is that enough?
Yeah, yeah.
Okay. Come on. One of these years, I'm trying to figure out actually how to project stuff. Other questions?
What is the, I know you said Wednesday and Thursday next week are test days. Are you lecturing on or Tuesday? Or what are we doing Tuesday?
I will start out with, are there any questions?
Okay.
If there are questions that take up the entire time, great.
Okay.
If there are not, I have material that I will go over.
And will that material be on the test the next day?
If it were, it would be just at a very simple level.
Okay. And the test is on what chapters?
Everything.
Oh, it's just everything.
The topics are energy, momentum, rotational motion, the harmonic motion. Those are the 4 main topics. That's pretty much what we covered since the last test.
Okay.
We're gonna probably, potentially, we're gonna hit some new stuff today.
That might be on there.
That might be on there, again, at a simple level. But those are the 4 topics where I feel free to ask you more difficult questions. And I would recommend that you go through the Rube-Goldberg test, of which the answers are posted, as well as I have a video of like going through the entire test. And again, I'm not saying that that's the test, I'm just saying that covers pretty much all the material. Other questions? Yeah, we'll start right there and I'll do questions as we go. All right, so I have a spring. I attach a 3 kilogram mass to it. It stretches out to, the spring is now 8 meters long and in equilibrium. I'm then gonna take that spring, put it on a horizontal frictionless surface, and then pull it out. Five meters. And I'm gonna be asking questions along the lines of, at what times is it gonna be at its maximum speed, or what times is it gonna be at its minimum speed? How fast is it going at 3 seconds, things like that. All right, so let's start out with, what's the spring constant?
We need to do formulas.
Okay, what formulas?
It's K equals force delta X, I'm forgetting, I don't think it's.
You're mixing some stuff up there, but you're hitting.
Yeah, it's the middle letter, I forget what letter it is, or force.
Let's go to the basics. In the equilibrium vertical position, vertical equilibrium position, what are the forces acting on the mass?
Weight,
And,
tension.
okay, more specifically, not just tension.
Oh, the spring?
Yeah. All right. So I got weight acting down, I got the spring acting up. It's in equilibrium. Substitution. What's the generic formula for force from a spring?
K. Oh, is it negative K? No.
Are you stopping there?
No, it's an equation, I'm trying to figure out the rest of it.
That's it. Now what's the negative mean?
Force equal.
In this particular case, opposite the direction of the displacement. So we have K delta X. So I'm not quite sure if you were thinking of this formula or the next one, Jack, but K therefore is mg divided by delta X. And let's not put this on Earth 2, let's keep it here. Some generic place on Earth 1. So at 3 times 9.8 divided by.
Which spring are we talking about, the 8th one? Or
I mean, that's the one where the mass is in equilibrium.
Oh, then it'd be, 6 meters. From.
Oh, I forgot the numbers I used over there, yes. So we end up with 4.9 units.
Newton meters?
The anti-Ed disease.
Huh?
Student years ago named Ed, who whenever he would give units, he would always put the word per in between them.
Yeah.
And so I called it Ed's disease. Later on, had his daughter in class and was calling it Ed's disease before I realized I was talking about her dad. He was an older student, by the way. It's not Newton meters. Yeah, Newton's per meter. Thus the anti-Ed disease. All right, so 4.9 Newtons per meter. And now I'll take the exact same spring and I put it horizontally. Because it is the same spring, I know that the spring constant will be the same. I stretch it out 5 meters and I let go. So from the information that we have here, so I know the value of K. I know the mass attached to it. To the point where I'm throwing markers, I don't feel like bending down. K is 4.9 newtons per meter. What can we figure out? It's an ideal spring. I guess it didn't say that explicitly. Hopefully we're thinking it. If it's an ideal spring, we've got a set of equations that automatically just sort of come forth.
The conservation of energy.
Oh, well, conservation of energy is gonna work, okay, so we know that however we set it up, E initial equals E final.
What are we looking for at the moment?
Anything that, if it's an ideal spring, we know the spring constant, what else do we know, or can we figure out?
Can we figure out the period
Okay, how do you figure out the period?
using the formula for the 2 pi root, 2 pi root LG?
No. What's wrong with the 2 pi square root LG? There's two things wrong with it. All right, what I heard him say was use the formula T equals 2 pi square root LG.
Oh, sorry. Over L over G.
All right, so that's one issue. What's the other issue? Why could this not be used here?
Is that the inverse of frequency?
That's not the problem.
I feel like it's L, but I could be wrong.
Say it again?
I feel like something's wrong with the L. Could be wrong. I don't know what I'm thinking.
We're not taking into account the spring constant in that formula?
What is this taken into account? I guess it comes down to when should you use this formula?
Is it about revolution?
When do you use this formula?
For timing stuff?
For what?
Oh, is it the pendulum?
Yes, it's the simple pendulum formula. If this thing's on if this is on a horizontal frictionless surface, the thing's oscillating back and forth like this, the acceleration due to gravity is irrelevant.
Okay.
So, yeah, this is for the simple pendulum. What is the period for an oscillating spring?
Is it K over N?
It's one of those two. Is it M over K or K over M?
K over
M
N.
over K.
And fine. All right, let's think about it this way. The period is how long it takes to oscillate back and forth. We got M and we have K. K is the stiffness constant, is how fast the thing's gonna snap back. M, basically we've got an inertial term there. If M is larger, is the period gonna go up or down? Yeah, the more mass, the longer it's gonna take. So M's on top. Or from the K point of view, if it is a stiffer spring, is it gonna snap back faster or less fast? Yeah, so if K goes up, the period goes down, K's on the bottom. All right, but speaking of which, what is the square root of K over M?
For this problem or just in general?
In general.
That is the,
GG?
Angular.
Go for it,
Angular frequency?
with great confidence.
Angular frequency?
That's great confidence.
Angular frequency.
There we go. Angular frequency. Have faith. Believe in yourself, even if you're wrong. All right. So we have those equations right there. Matter of fact, once you have this, there is a relationship. What is the relationship? Do it that way, between frequency and angular frequency.
Oh, I heard that inverse, operation.
Oh, you mean the reciprocal? Not between frequency and angular frequency.
Is it angular frequency? Angular frequency equals 2 pi frequency.
Yes. What is the reciprocal of frequency?
1 over,
Period. I guess I could have said, what's the formula, what else is equal to frequency?
1 over f equals period.
Yep, there we go. All right, and from these three things, you derive this. All right, so we have another set of equations also.
Yes, the cosine sine ones, no?
Yes, those ones.
So your position is equal to your amplitude cosine angular speed, the omega, so angular frequency t, and then your speed is equal to negative
That's
amplitude.
velocity.
Of velocity. Negative amplitude sine omega t.
You lost something there.
And
Negative amplitude omega.
Oh, negative.
And acceleration equals,
Negative amplitude omega squared cosine WT. Omega t.
all right. Once we establish the simple harmonic motion, boom, this is the ones that apply. If it's a simple pendulum, we have that other one that we can use mostly instead of these. All right, so in this particular case, let's see, we don't need this anymore. We'll save the conservation of energy for later. Why don't we start with omega? What is omega?
root k over n.
In this context, what is omega?
Angular frequency.
Yes.
Yeah.
All right, so I was looking for our actual numeric value. Okay, if you want to go that route, then what's that? Omega's gonna be easier to find first, because there's the formula.
I got 0.9036.
I got the same thing.
All right, units?
Hertz.
Angular hertz.
I've not run across that before, so let's just assume that no one has actually officially used that.
Which means I'm not totally wrong. Some hermit physicist out there might have been.
I suspect if you use the term angular hertz, they will look at you strangely, but know what you're talking about.
Just meters? No.
I think I heard you correctly, radians per second. It's the same as angular speed. All right, so we have omega now. So we could find regular frequency or what have you. Notice that we could also sort of combine these two things here. This would also be equal to 2 pi divided by omega. Or something that might look familiar for those who have had or are taking trig, omega is 2 pi divided by the period. Is that the one I want? Oh, no, that's the one that if you've had trig or are taking it, it'll look somewhat familiar.
She said no.
All right, so we know what omega is.
Let's do frequency next.
All right. What's the frequency?
W.
1.4195. I divided omega by 2 pi.
I got 0.779.
What'd you have?
1 point, oh wait, I might be in, is it supposed to be radians or degrees?
There's no unit conversion here.
Oh, well,
Doesn't matter.
Yep, 1.4195.
So frequency is omega divided by 2 pi, so that divided by 2 pi.
I got 0.1438.
That one makes more sense.
Yeah, I redid it. I did mine wrong, but
Okay.
that's what I got when I did.
Um,
Did it again.
I did the same thing I did on the last.
Thank you, Gigi, for setting them straight.